Michelson's interferometer, a common configuration for optical interferometry, was invented by the 19th to 20th century American physicist Albert Abraham Michelson. The Michelson interferometer is employed in many scientific experiments and became well known for its use by Michelson and Edward Morley in the famous Michelson-Morley experiment. The phenomenon of interference is used to make precise measurement of wavelength or distance. In Michelson interferometer, a beam of light from an extended source is divided into two parts of equal intensities by partial reflection and refraction. These beams travel two mutually perpendicular directions and come together after reflection from plane mirrors. The beams will overlap on each other and produce interference fringes. The setup is simple.
We have a lighthouse S, a converging lens L to make rays parallel.
The rays falls on glass plate G1, which is partially silvered. The plane mirrors M1 and M2. M1 is movable by means of screw. M2 we will keep the mirror fixed. The ray incident on the glass plate is partially reflected and partially transmitted at bottom surface of glass plate. The reflected ray green 1 travel through the glass plate and move towards mirror M1. The ray is reflected at M1 and retrace its path in glass plate G1 and emerges out the glass plate G1 and travel towards telescope. Ray transmitted through glass G1 represented by red ray travels straight towards mirror M2 and reflected back along straight path and is again reflected by bottom surface of glass plate and ME towards telescope. The reflected ray green 1 travels the 2 times through glass plate G1 while the red one didn't. Because of this the rays reaches telescope at different time. There is an extra path difference. To compensate this extra path difference, when compensating glass plate of same thickness as G1 is added in path of transmitted ray. When this compensating glass plate is added in the path between mirror M2 and glass 1 at sand angle of inclination 45 degree. This extra path difference is compensated. The rays reaches telescope together at telescope. These two beams are produced from a single source by division of amplitude and hence coherent. They may superpose to give an interference pattern. We can observe alternate dark and bright fringes. Fringe pattern like that of Newton ring and wedge can be obtained in this setup depending on how mirror M1 and M2 are oriented with respect to each other. If we look through the telescope, we see image of mirror M1 and virtual image of mirror M2, M2-. If mirror M1 and M2 are exactly perpendicular to each other. If two arms of interferometer are of equal length, that is mirror M1 and M2 are kept at equal distance and we look through the telescope image M2, M1 coincide. And we will observe concentric circular rings. Now if the interferometer arms are not at equal distance, the images M2 and M2- appear to be separated by distance d. The rays appear to be coming from two separate coherent light sources S1 and S2 separated by 2d distance. Ray S2 has phase difference pi. Path difference between beams equals 2d cos theta plus lambda by condition for brightness is that 2d cos theta plus lambda by 2 equals m lambda for given mirror separation d, wavelength, order m angle theta is a constant. Hence these are fringe of equal inclination. If M1 and virtual image M2 coincide, that is d equals 0, path difference is lambda by 2, that us interfering rays are out of phase. Hence we get a dark fringe. If one of the mirror moved lambda by 4 distance, path difference change by lambda. We get a maxima. Of again movie lambda by 4 distance, we get minima and so on. As we move one of mirror outward direction, more rings appears at center and already existing rings in periphery disappear. Similarly, if we are moving mirror towards glass plate G1, D becomes smaller and smaller, internal rings contracts and disappear with new rings simultaneously appearing in periphery. Just like concentric circular rings, it's possible to observe localized straight parallel fringes. For this two mirrors are kept titled with respect to each other. M1 and M2- will not be parallel but inclined with air-thin film between them. When mirrors M1 and M2 are not exactly parallel or not equally distant, a wedge-shaped film is formed between them. The path of two reflected rays, originating from the same incident ray Y reflection from M1 and M2 are no longer parallel. They intersect near M1 and hence the fringes are formed near M1. The fringes are called localized fringes, and to see them the eye must be focused on the vicinity of M1. These fringes are curved with their convex side toward the thin edge of the wedge as shown in the figure. The thin edge of the wedge is to the left and therefore the observer fringes are convex toward the left. As we go on decreasing the separation between M1 and M2, the fringes move across the field of view away from the thin edge of the wedge and at the same time gradually become straight. When M1 and M2 intersect, the lines are perfectly straight as shown in the figure. We have two wedges opposing each other, so the line should appear curved on both sides of the intersection, but for a small field of view, they appear straight. When M1 is still moved such that the mirror M1 and the virtual image M2 of mirror M2 get a position as shown in the figure, the fringes are again curved but with their convex side towards the right. Localized fringes become invisible for large path differences of the order of several millimeters. If the mirror is moved, fringe appear to move across field. If M1 move d distance, M fringes move across field of view. If we count the number of fringes move as M, we can determine wavelength by equation d equals m lambda by 2 or lambda equals 2d by m. Now, if we replace monochromatic light by white light, we can observe fringes with central dark fringe surrounded by few colored fringes. For observing this, mirrors lightly tilted and position of M1 where it intersect M2 is found. It's hard to find with white light. So, we first use monochromatic light and find the position where M1 and M2 intersect. Now replace the monochromatic light with white light source. Slowly moving M1 in this region using white light will bring the fringe into view. We get central dark and 8 to 10 colored fringes. These fringe useful to determine zero path differé. Fringe visibility describes how good the interference pattern is formed by the superimposition of two waves is, or how good we can distinguish between the bright and dim parts of the interference parts. Phase difference between the interfering waves must be 2n pi for maximum intensity and odd multiple of pu to observe a minimum intensity. If I max and I min are the maximum and minimum intensity respectively, then visibility can be written as L max, L min divided by L max plus I min. If we are using monochromatic light, then minimum intensity is 0. Then substituting in above equation we get visibility is 1. So, we can see fringes clearly if we use monochromatic light. If the light source we eyes is not strictly monochromatic, that is if consist of more than wavelength, then condition for maxima satisfied only for particular path difference. If for particular distance d, two interfering rays comes in phase, the fringes will be classy visible. And if rays are out of phase, intensity is minimum if two rays are of equal intensity. If not equal intensity, minimum intensity will not be 0. If two wavelengths have amplitude A1 and A2, we can express visibility A1 square minus A2 square divided by A1 square plus A2 square. If source is perfectly monochromatic, then the fringes will be clear, visibility will be maximum and constant for different value of path difference. Else d change with path difference.